velocity as an interpretation tool. And there are two things in it and uses of it that I'm going to talk to you about, okay? The first one has to do with how it can be used with trending and compaction state and stratigraphic prediction associated with sort of trend prediction. And the second one, I'm going to go through an example of how it can be used directly in terms of de-risking. In other words, let's look at the seismic imaging velocity as in what it means in terms of what type of lithology or fluid that we're dealing with. How many people, are there anyone here that's not familiar with the concept of seismic imaging velocity and what is with Ian? Anyone else? Okay, there are a couple others, okay. Okay, then I'll try to do you the very, very quick sort of explanation, is that in the process of getting a seismic image, that you need to go and have a rough estimate. When I mean rough estimate, with about, I don't know, 300 meters of vertical resolution, okay, of what the velocity function of the subsurface looks like, okay? And once you have this, you go and you try to image the data, okay, with this. And there are many different ways and approximations that end up getting used, okay? Time migration, pre-stack uses sort of a double radical and assumes sort of very smooth lateral variations in that velocity function. There are ones where you can go and have a more rapid variation, and that's pre-stack depth migration, but you have to do a ray tracing through the full model associated with that. Okay? But once you do this, that you look at all of the different offsets, okay, and how they've been restored that you're going to want to stack together, okay, in terms of that migrated gather. And if there's any mistake in that, you'll see that there's an event, but it's not going to be flat. And so there are some different update procedures you can do and different methodologies in order to go and figure out how you should correct that velocity function to make those flat, okay? So that you really are looking at sort of how well things are imaged and are using a metric of how well they're imaged to iterate on what that particular velocity function should be, okay? But this it's a velocity function. It's a model of the Earth with velocity, but has about 300 meter vertical resolution, okay? Which you remember seismic is maybe 10 meter resolution. Well logs get down to maybe 10 centimeter resolution, okay?
Is this the same as the stacking velocity?
Yes, but stacking velocity normally refers to things when you're using pre-stack time migration, but yeah.
That's sort of the crudest form of it, yes.
Yeah, it's the crudest form. I'm sorry, that'd be a post-stack. Yeah, that's the crudest form of this, yes.
Your underlying assumption there is that things have to be flat. Can you explain that a bit more?
Well, when I say that things need to be flat, it means that they need to be well imaged.
Oh, okay.
And you actually go and sort of form an image associated with different angles of incidence. And the fact that each of those images have to look identical is the criteria that you end up using.
They have to some. And if they're not at the same, if those images don't have their minimum at the same time, then they won't sum properly, so they won't image when they sum together. That's what I mean.
Okay, they don't necessarily have to be topographically flat.
No. And when I say flat, I mean flat as it's at the same point as a function of offset. Okay.
Flat refers to gathers becoming flat.
Right.
That's right. Yeah.
That's just a
Yeah, and it turns out that if you pre-stack time migration means that the geology should be roughly flat over the sort of the range that you have between the shot and the receiver is what the approximation is there.
The stacking velocity is it an RMS average of all velocity in all layers which the ray particles pass through?
Is that?
Yes.
Yeah.
Yes.
And so, I mean, that's just what we're talking about when we say the seismic imaging velocity. But, you know, how can we go and utilize that, okay? And so now let me go in and I'll talk a little bit about what we did in the earlier exercise. You know, obviously,
Mike.
yeah,
For the purposes of the camera, he needs you to move that a little toward the plant.
what?
A little
plant.
toward the plant,
The plant.
yeah. Then he'll see the whole thing. Right there.
A little more.
A little more?
A little more.
To the left, to the right.
Yeah, no, all right, no.
I feel like I'm having a picture tape.
Okay, all right. It's between those two gentlemen.
Thank you.
Thank you.
So anyways, that if I go, we went and we looked at some sands, and we ended up picking down here these particular intervals, and we picked the top and the base. We had the second well log associated with that. So we ended up having, let's say, density, VP, and then you also end up having VS, and obviously we looked at the other, and we also had the gamma log up here. And then we went and we said, okay, here's our intervals, here's the top and the base associated with each of these. And then I showed you right at the end that coming out of this, we ended up getting 3 different cross plots, okay, associated with this. And the 3 cross plots that we got associated with it is as a function of depth. We looked at the compressional velocity. Then as a function of compressional velocity, we looked at the density or the porosity. Okay, porosity for the reservoir member. But we could also equivalently look at it in terms of density. Then we looked at that in terms of, as a function of VP, we also looked at the particular VS. And one of these points here ends up being one point with an uncertainty on each one of these plots. And then we ended up getting quite a few of these points, okay? And then we would go and we end up fitting a particular line with an uncertainty around it for each one of these particular relationships. Okay. And we did this for both the shale, and we ended up having another set of these and fit lines that have to do with the sand. Okay? And I'm going to start at the bottom, okay? And that we're going to go and I'm going to sort of tell you a bit about what is found. That if you go and take a look at these relationships and compare, let's say, a relationship that is at one field to what we see globally, okay? And ask, what is the difference in this sort of standard deviation that you get locally versus globally for VP-VS relationships, okay? That you end up going and we'll find that things go from about 80 meters per second globally down to about 50 meters per second locally. But in terms of sort of absolute percentages, that's going from about 5 to 3% uncertainty on the value, okay? Where this again is the global and this is the local, okay? And this overall, you know, I consider, and if you take a look at the sensitivity in terms of what was contributing to your uncertainty and reflection coefficients, this really doesn't matter. I mean, this is not a thing. This is already small enough that it's not the major contributor, and changing from 5 to 3% is a fairly small change anyways, okay? So I would tend to go and say for this, I have an exclamation point. This is very good in terms of using sort of global relationships locally, okay? And that's another reason why that if you don't have shear logs, using these relationships is actually, you feel fairly confident about, okay? Now let's go up to the next one, okay, and ask the same questions about sort of what the changes are, okay? And in this particular case, that you characteristically find that things go from about 0.03 grams per cc in uncertainty down to about 0.01 gram per cc uncertainty. And so things are a little bit worse here. You go from about 12% down to about 3%, okay? So you end up seeing a larger variation, okay? I end up normally saying this is okay, but not great. In other words, that this type of uncertainty normally does not dominate, okay? But the relationships are not as robust, okay? And let me just sort of talk a little bit. Does anyone have any idea or explanation of why this may not be as good as VPVS? Or what could be changing to cause this to change and not this to change? Any suggestions?
Water. You get water fluid in your rock.
Fluid, okay, well.
Because it doesn't change the shear. So it
We'll
doesn't
assume
change-
that we've taken out any changes in terms of fluid differences.
Geological history.
Okay, geologic, well, what could be different about the
Just
geologic?
the age that is being buried and being brought back up to the surface. That's it.
That's probably for the next one. Keep that in mind, and we'll bring that back up for the next one. Because this ends up being sort of normalized, you know, this gets normalized out, because that ends up being a change in predominantly the VP, and moving along here would be sort of where you would change in terms of, you really don't care if you're sitting here where you were initially. It's sort of it's a depth VP coupling associated with that. That makes a big difference here. So we'll keep that for the next one. Anything else?
Texture?
Texture, okay? Or the architecture, I think, is what Dave used, okay? That is a very big thing, okay? And that's probably the dominant thing. And you say, well, why doesn't that go and change VPVS, okay? And I probably need to go and sort of refer you to actually some work that Dave and I did. But we were looking at just changing the texture by adding more fines. And it was remarkable that it actually caused a spread in this relationship, but does not cause a spread in this relationship. And you need to look at what the implications of that is in terms of some detailed physical models. But yes, that this ends up being caused predominantly by sort of texture or grain scale architectural differences, okay? I don't think that's widely known in the industry, I think, in terms of the differences between these two.
Is that paper in our references, Mike?
I'm
remember.
not sure. I'll double check if we actually reference it. Okay. Now let's get up to the main focus, which ends up being the predominant problem, which is the one at the top, okay? Now, I mean, this is just ridiculous. I mean, you go from 500 meters per second down to 80 meters per second, which goes from a 30% uncertainty down to the 2% uncertainty. And what's most important is that you'll see how we do the sensitivity analysis. This is the uncertainty, especially here, that tends to dominate over the dominate in terms of the causing the uncertainty and what the reflection coefficients are. And the more uncertainty, the more overlap, the more you could get confused the way that we were talking about, okay? And so, well, already, I mean, Mark, I mean, you ended up saying, okay, well, you could just have the same interval at a different depth, okay? Perfectly, that's one thing. First of all, let me just put down here, this is bad, okay? This can be caused, as he was saying, at sort of geologic uplift, okay? Uplift, so you compact it and then change it, okay? And in fact, I'll show you a really good example of that in a second, okay? Any other particular suggestions for what could be causing this?
Diagenetic change.
What?
Diagenetic change.
Diagenetic, okay, okay. geologic diagenesis. Okay, and not surprisingly, that's more of a problem in carbonate rocks because they tend to go through more diagenesis.
What does
A
diagenesis mean?
smectite boundary transition.
Yeah, diagenesis means this. If normally when you talk about rocks, the character of the structure of the rock, sedimentary rock, is determined by, initially at least, by the genetic setting of the rock. That is, where did it come from? How did it get laid down? Genesis, okay? Diagenetic means that genetic character has been altered. And how is it altered? Typically by, over time, groundwater moving through the rock, dissolving certain minerals, redepositing others, cementation, redeposition in limestone systems, so that the structure of a diagenetically altered carbonate rock doesn't look anything like the structure when the minerals were laid down at the seafloor.
And also the other one I was just talking about, there's a smectite-illite transition at a particular temperature in shale mineral, in clay minerals. And that you'll all of a sudden, at like one depth, will see it jump in it. And in fact, like Fourier-Kepler, the Nikika development, that almost all those fields is so hilarious that the shale above the reservoir, it's, smectite, and below it's illite. And
Right.
you have totally different trends above and below, which totally blows any sort of simple volumetric estimate, since your bounding shales on both sides are so different because they've gone through that diagenetic shift. Literally, they just go look like this, One is nice line, one's here, and there's an absolute jump right at the reservoir. So, but if you look at it, it's right at the smectite-illite transition point. Okay, diagenesis. Okay, one more I'm looking for.
Pressure.
Overpressure. Okay, whether or not you're normally or overpressure. Okay. Okay, normal versus overpressure. Okay, and okay, how many people here don't know what we're talking about when we say sort of overpressure?
Differential pressure.
What?
This is the differential.
Okay, wait a minute, don't be hesitant. I mean, I don't want you to look at me like, what the heck's overpressure?
Well, everything is normal pressure to me. I don't know what normal pressure is.
It's a very simple concept, okay? That if we're looking at, okay, a rock here, okay? Just imagine that we end up having sort of a particular piston on top of it, okay? And we have an ability, as Dave was talking about, to go and vent off the pore pressure here, okay, up to the surface, okay? And this is the pore pressure, okay? Okay, let me ask a question, okay? If there's a connected path, okay, from these pores up to the surface, okay, what is the pressure in the pores here? Okay? What's that? Yeah, but no, it's the weight of what? It's the weight of the water column, right? Okay?
OGH.
Okay, what happens if we close this off? What is the pore pressure?
The rock.
It's the weight of the rock, okay? Okay, if it's the weight of the water, that's called normal pressure, okay? If it is the weight of the rock, that's called overpressure, okay? Okay? And that, okay, now let me go and I'll ask you a question, okay? Which rock is going to be compacted more? The overpressured rock or the normally pressured rock? What's that? Normally pressured rock, exactly, okay? And so that shows up, okay? If I was going to go and have one of these trends, okay, is that you'll go and see that if this would end up being the normally pressured rock, okay, say this is normal, okay, at the same depth, if I end up being overpressured, it's going to be below that, okay? It's going to cause a downward shift if you're overpressured, okay? And if you ask, when does that happen, okay, it really happens, and you can see it right here, you have to have some barrier that doesn't allow the water to get to the surface. And so it's not very, it's very common when you end up getting good amounts of impermeable shales, okay? And by the way, this is the cause of, you know, the very dramatic, you know, red-adair blowouts and the like. If you drill into overpressure and you have this particular drill stem all at sort of water density, and now it has to be at rock density, what happens? Well, stuff comes shooting out because the pressure down here is rock pressure, it's not that. So drilling into overpressure is the problem. And normally too, when you go and drill, you'll go and case the hole right above here and increase the weight of the drilling fluid to that is much closer to rock density when you go into it, okay? And so I give you a little primer for the other people. I mean, it's kind of the petroleum people, I know are saying, man, this is old hat. And so overpressure, okay? And sensing overpressure can change the compaction state of the rock, okay? One other question, okay? If you have overpressure, is that good or bad for amplitude analysis? Okay? Is that good or a bad thing? Anything? What? What?
It reduces your velocity.
Okay, what happens if I'm overpressure, okay, is the beta of the rock, is it going to be more or less compacted rock? If I'm, it's less compact, okay? Beta's smaller, is that good or bad for telling for whether or not a fluid effect is? It's good, right? Okay? And so that if you're going, and a lot of times people have rules of thumb of depth, right? If you have strong overpressure, you're going to see amplitudes a lot deeper than you would have if it's normally pressured, okay? So using rules of depth thumb in overpressured environments, you can be very surprised. And it's very common in the Gulf of Mexico. You're saying, why are you seeing blooming amplitudes at 30,000 feet? Well, it's because your pore pressure is 20,000 psi because of very strong overpressure, okay, in those cases. I've sort of gone aside, but okay, now, okay, we have a problem, okay, we have a big problem. Houston, we have a problem. It's not just the recent hurricane. And, okay, what do we think the solution is going to be to this? Or okay, seismic imaging velocity. Okay?
Rest of the world, we solve those problems.
And okay, and I'll go and I'll give you the strong theorem and the weak theorem here. Okay, okay, strong theorem. Strong theorem is that the low frequency interval velocity, in other words, the 300-foot average interval velocity, okay, ends up being related to the shale VP, okay? Why is this strong? It's because most of the earth in these sedimentary basins are shale, okay? So the 300-foot average, other than there's an anisotropy correction of about 5-ish%, other than that, it ends up being that this particular 300-foot average of the low frequency interval velocity, which is this 300-meter average, ends up being fairly closely related to what the shale VP is, okay? Why is this important? Well, if we go out and do some imaging, we don't need a well, okay? We just need to have shot seismic data, and that will go and give us a fairly good idea of this. If we can relate this to this, okay, we can go and get a good estimate. And so what do we normally do? We end up going, and the thing that doesn't work very well is VP is equal to A plus B times depth. Okay, this is the bad stuff, where we get a very poor, but if we add a C times this low frequency interval velocity, that you end up finding there's a significant reduction in that standard deviation, many times down from 500 meters per second down to as little as 150 meters per second. And what's probably more important, you'll go and get the points beforehand will have all types of systematic variation in it. You know, if you go and look at the VP depth, and after, and this will go and have, if you look at the standard deviation, it's 500 meters per second. Then if you go and include this additional term in it, that you'll see now that the stuff will be more randomly distributed and end up having this as 150 meters per second, which is a much more acceptable uncertainty, okay? And in fact, you end up finding that C ends up being many times very close to 1 if you do that statistical fit, okay? And it equals 1 because the strong theorem is a strong theorem, that the two are effectively equal, okay? Okie doke? Okay, and so that's how we go and use that. I'll show you a good example of that, okay? What's that? A is just a number. It's a statistical fit number. You fit a line, those are the numbers associated with the fit of the line. We end up using an average. I mean, you could have different types of averaging procedures, but we normally just use them. But or many times you just go and if you have the seismic imaging velocity, you actually use the seismic imaging velocity itself. Okay. A little bit of perplexed looks. I mean, are people sort of understanding what I sort of have said here, or what? No. Okay. Again, it's sort of stated that what we want to do is to have some predictive ability of the compaction state, right? Okay. We want to know what the VP is of the rock, okay? But if we, in the case that if we know this varies a lot as we move around, okay? We need to know, we know it can be uplift, it can be diagenesis, it can be overpressure that can all cause the change in what the VP of that rock is. Okay. Luckily, if we have the seismic imaging velocity, you understand what the seismic imaging velocity is, right? Since that we can get that without having a well, it can vary pretty rapidly as you move around. And since we can relate this seismic imaging velocity to the compaction state, okay, we can now predict from the seismic imaging velocity what the VP is. Then we also have equations back here that, well, given the VP, we can predict using this what the density and what the DS is. We can then predict what the amplitude response is going to be, okay? But we needed to bootstrap ourselves and understand what the compaction state is underneath all these other things that could be changed. Okay. Is it clear to you now, or? Yeah. And the real thing is, and as Dave talked about, is sort of reducing the variance, okay? And you want to figure out the variance that's really contributing and then ask how do you go and reduce that, okay? And since this tends to be the predominant thing that's causing the variance in what your prediction is, you need to figure out a way to reduce that variance. And this particular strong theorem for shales is a very good trick and way of doing it, okay?
What are you gonna go into?
Sands? Yeah, that's the weak theorem. Okay, weak theorem, okay? The weak theorem is that Sand's compaction state is approximately equal to that of shales, okay? So we use the same type regression, which is the VP of the sand is equal to A plus B depth plus C, the low frequency interval velocity. Okay? Okay? And it's probably not surprising that the values of C end up being not 1, but about 0.6 on average. Okay? We end up seeing that we go from the 500 meters per second down to, let's say, 300 meters per second. So it's not as good as for the shales. Okay? Okay, what will violate the weak theorem, for instance? Okay? Thoughts? Think of the causes of this, okay? If you have uplift, well, that probably would be reasonably consistent because they'd be uplifted as a unit, right? Okay. What about your second thing, diagenesis? Yeah, well, why is diagenesis of the sand related to the shale? That could be violated, right? Okay. What about pressure? That's the third one. Could that be violated? Okay. Yeah, it can. And let me go and give you a little primer on this, okay? Is that, and it sort of goes, and some of you maybe have taken Glenn Bauer's pressure course. This is my sort of, his pressure course in a nutshell. That first one talking about overpressure. The second one has to do with this, is that if we go and look at the Earth and if we have a sand, okay, there are kind of two ways that the sand could look. One is the sand is going to look like this, okay? The other one is that the sand is going to go and look like this, okay? Okay? And, okay, if the particular sand ends up looking like this, one thing you have to think of is the sand is like a pipe, okay? And if the sand looks like this, it's going to pump pressure up, or the pressure at this point is going to be representative of the maximum pressure that's getting pumped down here, okay? So this is the particular pressure that matters, okay? If it actually sits like this is the pressure that matters, or you end up having something that's normally pressured here, okay? Or you can get a super overpressure here, because it's not only the weight of the rock here, it's actually the weight of the rock down to the deepest point to which it's connected, okay? And so that the basin, what I call the basin plumbing, can matter, okay? Or in other words, how these sands are connected around can end up mattering, okay? Those of you who've taken Glenn's course, he talks about the centroid, because it's really not the pressure down here, it's actually the pressure associated with the centroid of where the sand is. But, I think in general, I think in terms of whether or not you're plumbed deep or plumbed shallow, okay? Make the particular difference on these things, okay? So that actually causes some things to be violated, and there's a reason why it's more of a weak hypothesis, and does not, work as well, okay? Okay, any particular questions on this, or? Yeah. I see perplexed looks still, so.
I suppose, Mike, when you've got a lot of overpressure, I wonder sometimes, in terms of the sand properties, and how much sand you've got in the system, as to whether or not you can predict really whether or not the sands are going to behave like the shales are or not. Because I suppose if you've really got quite a sandy system and we think it's open, well then you're probably not going to have overpressure anyway, because the pressure is going to be released into the sands. But then if you've got a fairly isolated sand situation, I suppose you can then have a situation where the sand is basically plumbed to the surface, but you still could have a lot of overpressure in the shales. You got any, comments along those lines?
Dave,
Well, The problem you have is, how do you have the sand connected to the surface and the shale above and below it, in which it's encased, not? So if you have an isolated sand, what Mike's point is that if it's an isolated sand and it's enclosed in an overpressured shale, then the sand itself is a pipe, and it points of pressure between 2 points in that sand, the pressure will be able to be calculated by the density of the water or the fluid in that sand, rho GH difference in that sand. And so if it's, got structure on it, that's how you calculate. That's why he's talking about the pressure at the deepest point, which is the pressure, that fraction of the load borne by the water that's in the rock, overburden, less the rho GH of the water in the sand gives you the pressure of the fluid pressure at the top of that sand. But if you have a sand that is connected to the surface and the shale is overpressured around it, you can have such a thing, but obviously the shale near the sand is going to dewater into that sand, and that pipe's going to flow. It's going to take the water away. So you could have a very thick shale, and maybe the 100 foot or 50 feet closest to the sand above and below that's connected to the surface would not be overpressured. It would be, or very little overpressured.
Yeah, I mean, we've certainly observed that sort of effect. I think where we think there's probably a bit of overpressure. You've got a sand, and you get a change in shale properties, right?
Right, exactly, right near the sand. Exactly.
Sand shale.
And what's happening there, the whole way this overpressuring happens is that the shales, at least in these uniformly, basins which are being uniformly buried, is you have these fine-grained rocks, shales and siltstones, which have very low permeability. And they are being buried so fast because you have an Amazon River or a Mississippi River dumping crud on top at a tremendous rate. They get buried so fast, they haven't got time to release the water in them as they get squeezed with the low permeability these rocks have. So if you have a big thick package of shale that has no permeability and you start dumping a big load on top of it, it can't release all the water as fast as it's being buried. That's how it gets overpressured. And that's why you would see what we're talking about, what Guy just said. You have this sand, the property of the shale right next to the sand may vary. You'd see the acoustic property change. It would be harder, acoustically harder, higher velocity near the sand, which is more like overpressure, that higher differential pressure, and it would get softer, higher transit time as you move away from that sand body. It's dewatering into the sand. Sand is taking away that stress for the shale near the water. And at a point 500 feet or 150 feet above the sand, you could have a much softer shale acoustically because it can't release the water fast enough. It's got a long time constant to force water out through that very impermeable pipe.
Yeah, I think that what Dave has been talking about and Guy's been talking about accentuates. I've given a highly simplified picture here, okay?
Right.
That, these particular things, for those who don't know, that this is pressure diffusion. Even in the sand, it's a pressure diffusion equation. You have different diffusion. You'll go and put in the profiles of how much you can diffuse. You put in also, how fast you're putting stuff on. And there's a full simulation done to predict as a function of position what the pressure is. This is just sort of highly stylized. But in the end, what matters, okay, really is if I go and add this extra term, does the standard deviation decrease and does systematic scatter in the data disappear, okay? I've given you reasoning behind something, but there's a large amount of practical information that says regress everything you could think of against VP. It turns out that low frequency interval velocity is the best. It's a very practical thing. And, I've gone back and sort of talking about, with my two theorems, probably why it works as well as it does, okay? But what you really want to see is what's demonstrated up here on the screen, okay? And that there are sands and shale points, and I've done a simple regression against linear regression against depth, okay? And this is what you said that the prediction is from the regression versus what the VP actually is. And what you end up seeing is that, especially for the shale rocks here, that if you look at it a little bit more carefully, you see different wells end up having sort of different subtrends, and there's a lot of and this is what we call about systematic variation. That this is a different trend than this, and we're putting them all together, and we get this huge uncertainty, which is what 500 feet per second, which is up around 150, 200 meters per second. Okay. And then if we go and add this low frequency interval velocity, okay, that we end up seeing that for the siltstone, where we really had the problems with these systematics, that things go from 500 feet per second down to 300 feet per second, 100 meters per second, okay? But also notice that the systematic variation has disappeared, okay? It ends up being random, okay? That's the really important part. Not only, it's good to see this shrink, but when you see systematic variation disappear, it means you probably are capturing something, okay? And this case, Mark, is exactly what you were talking about, is that these wells each intersected the same section at different depths. And it's actually out in the Carnarvon Basin. And you know that stuff has gotten buried and has gotten skewed, and you were actually going through. And in fact, this point equals that point. This has actually been, this has been uplifted more than that point has been. Okay, and the actual compaction curves go by linking this to this and this to this in terms of how things go versus depth. So there's stratigraphic variation associated with also the depth of the burial on top of it. Okay, and that's actually shown on the next slide, of where if you took a look at the sands, those are, fairly, from well to well, those are fairly good. But if you start taking a look at the shales, you start seeing each one has the same form, but, they're shifted from each other. There's a systematic associated with the wells there, okay? Which is both a compaction as well as a stratigraphic variation effect, okay? Okey-doke. That's sort of part A, okay? Now let me go into part B. And this may be of interest to you, those in the petroleum division, because the example I'm going to show you is the Taroa prospect in the Falklands. I actually I was a little bit late today because I was talking to the Falklands asset team about this very case, because they're having a TCM coming up next Tuesday. And this is going to be talking about the advantage of directly using the interval velocity as an interpretation tool, okay? Dave, you shook your head, or?
No, I'm just trying to get rid of this pain on my back.
Oh, okay. And so we ended up going, and I'll talk a bit later on about how we do this, but given these particular trends and the different formulas that David talked about, you can go and get, in this case, what the brine, the oil, the gas sand should look like in terms of the reflection coefficients. You also have a fairly large uncertainty here because this is a new basin where wells have not been drilled. I think, though, an important thing here are predicted rock properties in terms of VP. And I've referenced everything according to the shale velocity. You see that the brine velocity of a brine sand is very close to the shale velocity, but oil and gas sands should both be slower by about 7 to 10%, okay? And so that's a good number to keep in mind, that, okay, hydrocarbons, sands should be slower, okay? And if you have about 300 meters, which is the, sort of the averaging effect, you should go and be able to see this effect.
How much data do you have to correct this?
That we ended up going, and this is where we ended up having to bring that from the northern Falklands, and where some of the wells have been drilled. So we were coming in from about 150 kilometers away. We also looked for consistency with predictions actually from the other side of the Atlantic, but that were probably genetically similar from the time of deposition, because that's been spreading apart, and those rocks are initially the same, and the history of those rocks are roughly similar on opposite sides of the ocean. So we can go and we can talk a bit more about that. That's a very good question. Okay. And there's also another particular thing to sort of remember in the back of your mind as you go through this, but it is very important. This is another good example of it. Not only is seismic imaging velocity an extra piece of information, but also keeping in this probably a catchphrase to remember is that independent pieces of information add together non-linearly, okay? In other words, if we go and have something like seismic amplitudes, if we have something like seismic imaging velocity, if we have something like CSEM data that or measurements that don't depend on each other, okay? That if you go and say that I have two pieces of information, what do we mean when we say nonlinear? That isn't twice as good. That's 4 times as good, okay? If we have 3 pieces of information, that's not 3 times as good, that's 8 times as good, okay? And you find out fairly quickly that it does not really matter a lot. It's only logarithmically dependent on the amount of the strength of each piece of information. It ends up being linearly dependent on the number of pieces of information you have. So remember, pieces of information add together non-linear if they're independent, okay? And so now let me go to the next part and start walking you through this. Okay, I think this is a good one for you, Ian. Ian, you're there? Okay. That this is actually originally processed seismic data, okay? This is sort of standard spec processing, okay? And you look at that and say, oh, good events, things are good, cum matata, no worries, as you'd say down here. Well, this is what happens when you go and process it properly, okay? And sort of what we call to the gold standard. And, okay, well, there's a pretty big difference because this now looks different, okay? That happens to be the target. Yeah?
What is CSEM?
Oh, that's controlled source E&M. Well, it's, well, actually the guys to your right is probably one of the world. Well, actually the group to your right is probably some of the world experts on that technology. It's essentially E&M radio waves, right? And you end up going along with, you pretty much think of it like a seismic survey. You tow an E&M source, not a seismic source, along the ocean bottom, and you have a whole bunch of receivers down, and you end up getting an image of the Earth, but this time it's going to be in terms of its electrical resistivity. So it ends up being sort of representative of the resistivity.
Well, it's an EM survey.
It's an E&M survey. CS means controlled source, so that you actually have this controlled source. Because most of a lot of the traditional methods end up using extraterrestrial sources of the waves. And one to your left too. I'm sorry. But what you end up noticing though is that this is really different now. It stands out as an anomaly. You also see things change at this depth where they did not before. Okay. Okay, there's the Jenny Craig before and after, okay? And we were talking about AB. Well, the AB ratio is dramatically different there than it was before, okay? That's probably, it's an imaging issue. Or yeah. Okay, now let's go and take a look at the particular objective, which is sitting here. And if you took a look at that in detail of where that objective is, you end up seeing that the velocity where you associated with this highly reflected package is 7% less than the velocity of the candidate shale above it, okay? Okay, that's a piece of information. It also matches the expectation that we had on that earlier slide, okay? And so this also demonstrates to you sort of the average resolution of one of these, of one of the imaging velocities. The seismic resolution, as you can sort of see, is representative as sort of the loop-to-loop thickness here. You can see that the resolution of the imaging velocity is probably about the thickness of my fingers. This is 6.6 kilometers, so that's probably about 500 meters per division, I think. Okay, and so that we're looking at about 300 meters resolution as advertised. Okay, 300 to 500 meters resolution. Okay, piece of information one. Okay, and then let's see. I just actually went and sort of, you can look at these things in terms of some of the internal diagnostics. These are sort of, they're little semblances. They're sort of telling you at what velocity are things flat. And you can sort of see the particular resolution is really the distance between these blobs, which is the distance between significant reflectors. And then you end up having derived from that a particular velocity. And you can see that the velocity does decrease from here down to here, just between the reflectors associated with the top and the base of the candidate reservoir package. And so you feel that that's not just sort of something that's fake at that point. And it's also very consistent there's not just one particular position. Also, if you took a look at, this is the CSEM anomaly and the resistive anomaly, you found that there were resistive anomalies of about, those of you who are used to reading petroleum well logs, this should be a nice comfortable number for you associated with what the resistivity of pays are. And there is a particular technical reason why this is a bit above the target that I'm not going to get into here, and you can discuss with the people on either side of you later. And in fact, if we isolated it and said that it had to be within the objective package, it's an even more comfortable number. In fact, it's a number that probably indicates fairly good reservoir quality and low SWs, in fact, low water saturations. Okay. This also is true if you take a look at a strike line through it. I don't know. I've been in petroleum too long. Looking at this, that actually looks like Mike Yeager's mustache. So.
Is that on the video?
Uh-oh, I'm going to delete it. So. I almost had enough guts to put and superimpose a picture of him on top of this when I presented it to him, but didn't. And also the anomaly in terms of the CSEM anomaly also ends up fitting structure, because we had actually a cross line as well as the dip line. You end up thinking this is what we think is a fluid contact, this is up dip. You see there's an anomaly here and here. It turns out that we think the structural closure goes across here with less sand here than here. This is a...
Okay.
Okay, what was the question then?
David asked you to go back to the last
No, it's okay. He's ready to go now.
Yeah, okay. Now the next thing is what's happened with the particular amplitudes on this. And that what's kind of nice is that there is what looks to be a totally water-wet delta that goes across the top of here, okay? That we know is not in closure, and we can see how it would have to leak. And then we have the candidate section coming down here. And what's kind of nice about it is that we can go, and this is the amplitude of the water-wet delta that doesn't change in green, okay? Which is a nice background, and that's actually a sand background. We could have gone in reference to a shale. And you'll see in a second where the shale level is, though. And so that now you see in this area, there tends to be one amplitude. Right around here, you go down to a second amplitude. Then you go down to a third amplitude, and the third amplitude is pretty much identical to the water-wet delta on top of it. And it actually shales out here, and you can see the difference between the shale to the sand sort of level there is sort of what you surmise. And And this is starting to look a bit like one of Dave's pictures, I think.
Yeah.
Did you see any flat spots?
Yeah, we'll get to that. And anyways, that's just showing you which one's which, and also just the two package breakdown. There actually is we normalized also to another one shallower up in a different area, which actually does have a fairly obvious flat in it, but it tends to be, that one's too shallow to be of interest. Anyways, that was called a gas water, but right now we're thinking it's gas oil, because it turns out that this is too much column height for gas. But this is about the seal capacity for gas, as it turns out, in terms of column height. So things end up making sense to say this is gas and that's oil in terms of seal capacity associated with it. So that's another thing. But you also can see to the left here, here's the range of expectation of brine, shale, oil, and gas. And you can see that the shale is down here, potentially. The brine is in the middle of the brine. The oil comes out in the middle of the oil, and the gas comes out in the middle of the gas. But you do realize there are differences, there are overlap in this, and you do worry about some net to gross changes. And you can even see here some possible stratigraphic variation going from here to here, so that could be confused with it.
So your nearest well control is 150 kilometers?
Yeah.
So yeah, then you would worry a lot about not knowing if it's laminated or not. You would have
Yeah.
no clue.
That's right, yeah. And but one nice thing about it is that if we go and take a look here as we go through, here's where the potential fluid contact is. And this is an isopack, so it's telling you how thick it is. And you can see there isn't much change in the isopack as you're actually going through this potential fluid contact, okay? If you now go and take a look though at the amplitude, that you do see a consistent amplitude change. In fact, this is probably higher net to gross, better sand. So you see that this is brighter than this is. But if you take a look at the ratio of this to this, and the ratio of this to this end up being the same. So going back to that previous viewpoint, this may be 50% net to gross going from here to here. This looks like this, but this actually has the same ratio, okay? So that the fact that you always get the same ratio, and in this, and that geologically you expect this to be very similar to this, ends up sort of helping out in terms of that. This is where, if you take a look at, most of the time we take a look at fit to structure as something different. We've gone here and taken stock, okay? We see a velocity anomaly. We see a CSEM anomaly. We see an amplitude strength anomaly, okay? Now there's an additional thing, which is how well does this thing fit structure, okay? And it turns out this is the near stack, but let me show you what happens as you go to the far stack. Let's go back and forth, and I would go and look at this line especially. And that it turns out that when you go and do your depth conversion, these 3 points that are separated by, I think, about 30 kilometers end up coming in at the same depth to within 20 meters. So, and also we were talking about flats. I mean, we did take a bit more of a closer look at these, that you do start seeing some evidence of at least feather zone in some of the far stacks, for instance. And that's really where he's talking about, is where Dave drew that picture of a fluid contact going through a sand, and you can sort of see, you know, in that case, a bit of the feather. And again, I think right here you can sort of see some of the phasing, especially of the lower loop, that ends up being a little bit of evidence of it, but it's a little bit of, you know, sort of thing.
So this is like 2D time data?
It's 2D time migrated, yeah.
What
But
about
it ends up being a real monoclonal dip, so it's not extremely complex, you know, sort of structures.
What about your oil, your hypothetical oil gas contact? Did you look at that on?
I think that they probably have since then. We didn't at this point. But this is, again, sort of the pieces of data adding together sort of non-linearly. This started off with the geologists and the petroleum systems. You added velocity, and that's the seismic imaging velocity, and you ended up seeing a bit of an increase in the oil and gas probability. The strength of the seismic amplitudes and the fit to structure, increasing things sizably more, and the controlled source E&M then increasing it even more, okay? And it was kind of an interesting, I think, sort of dialogue, because people got very uncomfortable with this, because you probably realize this is not the point of minimum accountability. And people try to go in and sort of change numbers, right, and bring that down. But they've sort of, and I think that it was Richard King that said, no matter how much I change these numbers, it always comes up with a big probability. Well, the one thing he wasn't changing was the number of times we did this, okay? And so you can go and twiddle around with details of exactly how the boost is done at each point. But the fact that you have a lot of these things adding together makes it a fairly robust prediction in terms of where you end up coming out. And so, remember, independent pieces of information, you went and each one of these you could pick apart and find failure mechanisms, but every time you find a failure mechanism, it's not consistent with one of the other measurements. And so you sort of hem yourself in with the independent pieces of information to where you get a really good sort of solid probability.
So tell me, did you boost the boost? So in between, so you went from, say if you went from geologic to velocity, you gave it a small boost.
Yeah.
And then went from velocity to amplitude. Did you boost the velocity component as well, or did you go back and do the original?
Well, there's a commutation. It doesn't matter what order you do these in. You go and you literally do boost the boost. Okay, I mean you boost it, then you boost it from here to here, right? But that is the sort of the proper thing mathematically. In fact, if you switch the orders of these, you'd still reach the same point if you ended up having them. But it's a representation that they're independent pieces of information. Yeah. I mean, what you're looking skeptical.
The answer is they're sequential, as he's done.
I feel comfortable with one boost step, but just the assumptions that go into comes back to what you said the other day, that the underlying assumptions could be totally wrong.
Well, the assumption that would be wrong, that would make the sequential boost. I mean, it's a very powerful thing we're doing.
I'm not saying.
And the one thing that would the assumption that I've always been very careful to state is the word independent. Okay, it's the exact wrong thing to do if these are dependent measurements.
Yeah.
Okay, and you're making a huge mistake if they're dependent. And so the assumption that you have to very carefully think about is whether or not these are independent pieces of information.
And not questioning the fact that these boosts are mutually exclusive. It's just that the geological inputs is, there's uncertainty around the initial input.
Yeah. Well, I'll tell you what, we doubled and halved it, and you still got the same answer. I mean, that's what I was talking about, an insensitivity, okay? That you're not that sensitive. You can have these initial probabilities, and you find that you may only decrease these probabilities from, what's an integrated 60% down to 50% by having the initial geologic risk, okay? That's what I mean, it's only logarithmically dependent on what these numbers were, okay? I think, I understand now where your discomfort's coming from, but it ends up being relatively insensitive to exactly what the geologic risk was, okay? And I can go through the spreadsheets and I would say, play around with it. You'll see if you have or double those initial risks, you're still sitting in the same place.
This work far and away overrides poor geological risk in a sense, because it's driven by the amplitudes.
Well, it's driven by the remote sensing information that, it goes and plays down the sensitivity on those geologic risks. And, it still makes a difference whether or not this is 1%. It'll make a difference on whether or not it's 1 or 10 or 50, okay? But it's really is going to decrease the importance between whether or not it's 20 or 40, okay? A factor of 2 won't matter, a factor of 10 will, okay? And I think that many times we're arguing about geologic risk at that last 50% can make a difference in the decision threshold, where here, it doesn't, because the remote sensing information starts taking over. And you'd have to change the geologic risk by factors of 10. I think normally you can get consensus on whether or not you're dealing with a 50%, 10%, or 1% prospect.
Well, mechanics are a bit of an issue in this area. Is that being considered in terms of velocity effect of volcanoes or the amplitude effect?
Yeah, it turns out the volcanics, and we know where they are, end up being highly resistive, and also they get to be really, really fast. And so we did take a look at that, but it was very inconsistent with both the resistivity profile and the imaging velocity profile. In fact, we did point on one of the prospects was we think definitely is a volcanics, and also it ends up being the wrong polarity too, because the volcanics will be hard. So I mean, we have examined the failure cases in this case with volcanics, and there are actually 3 pieces of information that contradict them.
Well, you couldn't start this off with a big chance volcanics in the original geology, and these 3 pieces of information to kill that.
Yeah.
Squeeze it down to the top.
Yeah, and also sort of, what probably is the one sort of failure mechanism we do worry about from time to time, but there's also AVO that contradicts that, is Mr. Cole. Because this is a deltaic sequence, and there could be, the one thing that's probably most likely in terms of stratigraphic setting is a coal, and it's a solid, but it has a different AVO than what we observed. It also would be resistive too. So it ends up hitting a lot of the positive bells, and it's only because of the AVO response that you can ameliorate it. But that's, that's probably the one that's not explicitly here. That's probably more relevant than volcanics in this particular setting.
So what can happen that would destroy your AVO ability to do an AVO, so that you couldn't tell
that's the
between a gas
question.
and
That's the question.
Yeah, I mean, I think that you're looking at poor processing, the fact that we don't have good well calibration, and you'll see that AVO is very hard to calibrate.
Right.
And
Come up to that.
and that I think that not having a good solid calibration of the AVO could contribute to that.
It'd be worth going out there and looking at it.
Yeah. But also, I mean, I think that one thing too is that, and it sort of goes back to the sort of why, this does cause discomfort, right, in terms of this large probability. But the flip side is that if this is not successful, that there has to be a very good reason why, and that, we will go and correct the mechanism, and people will be coming looking for me, even though I'm in the mining division. I can pretty much guarantee that, both Rob Pasco and myself. Probably, I haven't moved on quick enough, but anyway.
Mike, how much was the, you think, the resistivity out from being a volcanic?
The volcanics we saw get up into the hundreds of ohm meters.
Okay, I mean, I'm just wondering,
So it can be.
I'm just wondering, is it...
It could be thin volcanic.
Is it possible that the CCM is giving a boost mainly, because of it being resistive? And that, like you're saying, is independent from the amplitude.
Mm-hmm.
I'm just wondering that if you knocked it back on the amplitude, because we're saying it's wrong polarity, but you had a thin, interbedded volcanic sequence, what type of boost then would you expect for the CCM to give?
I never need to go and rework that. And if it's actually thin interbedded, it would probably be boosting the volcanics.
Right.
Equivalent to the hydrocarbon sands. would be my expectation. But it'd have to be thin here, because if it was thick enough to be resolved by the CSCM, it would, I can show you an example where we're fairly certain it's volcanic resistivity.
Sure, I mean, I'm not suggesting that
Yeah.
we would expect it, because I think we're fairly confident that on the basis of polarity that it's not a volcanic. But I mean, we are saying that they're two independent parts of information. So the CCM itself is really giving a big boost. And I would have thought, even if we deemed it because of the polarity, etc., being
Yeah,
down, that the CCM
it would carry the ratio of
Yeah.
volcanic to pay would be carried up and be both would be boosted together. That would be true.
I give you a long way
Crystal
where
is
you
resonant.
don't have all your, you had coal,
Something that's resonant.
boost velocity, some of those things would be negative. But when you add it together, you don't get a low result.
That is correct, yeah. I mean, the particular volcanic in this case, I think, would be significantly contained. I mean, I think that going and emitting particular coal would probably, I mean, right now that we probably think that's the most likely failure mechanism. You know, that's not the failure. It's probably coal.
Let's go shoot some seismic done.
You got three now. Some of them can be explained by others.
That's correct. Yeah, that's true. And I encourage the type of conversations around coal and volcanics we've been having, because as I talked about before, not risking those models is our most common mistake. And these should be the type dialogues we have.
It's thick. It doesn't have that big of a loss. It's zero side.
And I, you know,
What does this probability say about quantity? How do you interpret that in terms of whether the pain is large or small? Or, I think
we'll get on. We'll be getting to that. So.
Is that sort of inbuilt into that, or is it a separate analysis?
No, there was an analysis that went on that you probably, I breezed past one thing in the, I never talked about this. This is actually the net sand, and that net sand ends up being related to the amount of volume. So at the time I extracted the amplitudes, I was also making another extraction that actually has more to do with the volumetrics. And so there was, and we'll get into the guts of this and volumetric estimates, and you'll be doing that.
I guess I mean to interpret that when it says 60% chance of getting.
Oh, okay. Yeah, the way that you want to go, and we talk about risk and uncertainty, and I'll take a moment to talk about it. That mostly in petroleum, and especially in an exploration setting, that if you take a look at what you think the volume of hydrocarbon is, okay? This is sort of the volume of oil, okay? It turns out that it ends up being highly this is the probability of having that volume. It ends up to be highly bimolar. There's a big spike here at the origin, having nothing. Then it comes out, and you end up getting some distribution of if you do find something, okay? And so that normally we call this the risk, okay, is associated with the probability that's in here. And then we say there's a second distribution, or it's really bimodal. And the probability associated with this little hump around zero, okay, we end up calling the risk, okay? And then the amount around here we call the uncertainty, okay? In the volumes once we end up having it. And so the wheel of fortune, okay, that you're looking at, the wheel of fortune has to do with the risk, okay? And then you'll see a volumetric distributions that I showed in the first lecture have to do with the uncertainty and the volumes in the success case, okay? It's something really important to keep in mind, and I think even a lot of people within petroleum the petroleum industry sometimes lose sight of this difference. So.